Hey everyone, and welcome to my first video on seed finding and reverse engineering. Uh, this will be the first video in a series containing about 3-4 videos. Um, and but before I want to get into it, I just want to tell everyone thank you for subscribing recently. Uh, and I also wanted to say that more directly Minecraft content is coming soon to this channel. Thanks to Geosquare, I have recently been able to get myself better editing software, which hopefully should allow me to produce more actual Minecraft content for you guys. But today, we're going to have a lecture on linear congruential generators. And we're going to establish in this lecture a few basic formulas concerning these generators so that I can refer back to them in my later videos and in my Minecraft content. And I do want to say, even though we're not going to be playing any Minecraft today, this is very much at the heart of everything that I do in Minecraft. So if you want to truly understand stuff on this deeper level about the sort of stuff that my particular friend group does in Minecraft, this video is a pretty good place to start, I'm hoping. Anyway, let's get into it, right? So as I'm sure all of you know, Minecraft is built on this sort of attempt to feel organically random, right? So every time you create a new world, you're faced with challenges and terrain that you've never seen before. And the thing is that Minecraft, being a video game, has to run on a completely deterministic machine. And so what I mean by that is that if you know the state of everything in your computer when you start it up, and the computer's in a suitably closed environment, you can predict exactly what will happen in your computer. So programmers of things like Minecraft are faced with this real challenge, which is how can you create random behavior on a completely deterministic machine? And so the number one solution to this is to just fake it, right? So the way that we fake it is called a pseudo-random number generator. And a pseudo-random number generator is exactly what it sounds like. It's something that behaves predictably, but to any human looking at the numbers that it spits out, the human won't be able to tell that there's any pattern in those numbers that are spat out by the generator. And in particular, the Minecraft developers chose, well, at least in the Java edition of the game, chose to use sort of the default Java solution to pseudo-random number generation, which is a type of pseudo-random number generator called a linear congruential generator. And just so that I don't need to say these long phrases anymore throughout the video, if I have to refer back to pseudo-random number generators, I'll call them either PRNGs to make clear the pseudo-random, or I'll call them RNG because that's really the more common term. Although I would really stress nothing that we're dealing with here is random at all. And likewise, I'll refer to linear congruential generators as LCGs. So if we want to understand and predict Minecraft randomness, if we want to find seeds, if we want to crack seeds, we have to understand linear congruential generators because that's how Minecraft does it. That's almost everything that runs under the hood is a linear congruential generator. So what I mean by a linear congruential generator is actually a super simple concept, right? And it tells you right in the name what it is. And that's this formula that I have written here, right? So first thing we need to understand is that there is a number called the seed of linear congruential generator. And the seed is just any number as like a starting state, right? That's where the name seed comes from because the sequence of random numbers grows from the seed as you move along. And every single time you query the linear congruential generator for a new random number, it updates the seed as follows. first thing it does is it multiplies the seed by some constant a. So a never changes. So when you have a linear congruential generator, when you're first making it, you tell it what to multiply the seed by each step. Then it adds some b to it at each step. And then finally, to prevent the numbers from getting too big, it takes the remainder after division by m. And that's what my little mod symbol down there means. Right? So all I've just done there was read out in words what we have written on screen there. Seed is assigned. I'm using that little, if you've never seen that before, the equals and colon, that means is assigned. So you can just read it as such. And a times seed plus b modulo m. So that, once again, update seed to a times itself plus b, and then take the remainder after dividing by m. And yeah, and that's of course where the names come from, right? If you've been through a pre-algebra class, you know the linear equation form, y equals mx plus b. It gets drilled into everyone's head in middle school. And it's also called congruential because of this mod m on the right-hand side, right? So that's a bit of a fancy term, but it just means that we have a modulo m present. And yeah, so linear congruential generators refer to this entire class of random number generator, where you have an a, a b, and an m all pre-chosen, and then you generate random numbers accordingly via that formula. I should mention, perhaps this wasn't clear, the seed is your random number that you're getting out of this thing. That's what you would get if you call a linear congruential generator. It updates the seed and it tells you the new updated seed. And yeah, and you can then mutilate the seed however you see fit to gain a random number. We'll talk a bit more about that in a minute. But Minecraft doesn't use arbitrary a, b, m. Minecraft makes the same exact choice for a, b, and m basically everywhere in the code. There's two places where it uses a different a, b, and m. And that particular choice is because that's what the Java programming language does. So Java provides a class called java.util.random. And that class is under the hood. It's running a linear congruential generator. And it's made a choice for an a, a b, and an m. And every time you query Java for a random number, Java will take whatever seed it's currently got inside at the moment, update it accordingly, give you a random number, but that's what's going on under the hood. I do want to stress, though, that being able to deal with arbitrary LCGs is still important. It's very good to understand. So even though this video, because of the nature of Minecraft, is going to be focused on JavaRandom, everything I say here, with maybe one exception, applies to linear congruential generators in general. JavaRandom's not especially special when it comes to the theory. So let's get into how JavaRandom itself is implemented. So as I said, under the hood of the random number generator Java provides, there's a central LCG, which is called next, just in the code. That's the name inside the code. And next has made a choice for a, b, and the modulus m, as I called it on the previous slide, right? Back here, a, b, and m. And you see how the equation on the top has the same form. Seed is assigned around 25 billion times seed plus 11, and then divide by 2 to the 48th power and look at the remainder. That's all that's saying. And so here is I put in a seed, that massive number starting with looks like about 157 trillion. I multiplied it by that huge A. I added that little b, and I took it all modulo 2 to the 48, and we got the next number in the sequence. And then you put that in, you get the next number in the sequence. And you can see, as a human, there's not really many patterns going on here, at least looking at these three numbers. And it turns out that's not quite true, right? Because if you take a little bit of a closer look at this, you're going to see that the numbers in JavaRandom have this terrible problem where they alternate between even and odd. So you can see that's even the case in my sample output. It starts out as odd, and then you multiply odd number times an odd number, that's odd, plus an odd number, that's even, modulo an even number, that's also even. And so odd gets sent to even, always. And likewise, even will always get set to odd. You can convince yourself of that. And in general, it's not just even or odd, but it's also the remainder mod 4, the remainder mod 8. That is to say, if you write these numbers out in binary in base 2, right? Just the bottom bits tend to repeat, with a much smaller cycle than the large bits. I should mention, LCGs do eventually repeat. Because if you think about it, there's only finitely many options for what seed can be, because it's always taken as a remainder mod 2 to the 48. And since remainders after division by 2 to the 48 can't be bigger than 2 to the 48, we have at most 2 to the 48 options for what our internal seed can be at any given time. So eventually, after you run this 2 to the 48 times, you're actually guaranteed to get back to where you started. But the case is even worse in these bottom bits, right? Because it takes only 3 calls to get back, to go odd, even, back to odd again. And mod 4, I think mod 4 will also take only either 3 or 5 to get back. It's unimportant exactly how many. But the point is that the lower bits repeat much more frequently than the upper bits do. And to get around this, the Java programming language, because they're very much aware of this flaw, whenever you ask JavaRandom for the random number, it never tells you the whole seed. Instead, it will at most use the top 32 bits, so the ones that don't repeat very often, to make you a random number. And so down below, I've written out the very first seed, this 157 trillion thing. I've written this out in binary, and I've highlighted in red the bits that JavaRandom's going to store and it's going to use in the formula for the LCG, but the bits in black are what the user gets sent as their random number, usually. And in fact, the situation is a little bit more complicated than that. JavaRandom provides a number of methods, right? Because sometimes you want a random number between, 1 and 5. Sometimes you want just a random massive number. Other times you want a random number between 0 and 1, but you want it to be a decimal. And so JavaRandom gives a bunch of different methods for generating random numbers. These 5 are the ones that you see in Minecraft's code. There's 2 others that are kind of important. They're called next Boolean and next Gaussian, but they're not so much used in Minecraft code, or they're already a case of one of the ones that already exists. So yeah, let's just quickly go over them, because it's not super important to know what all these are, but we've got next long, which gives us a 64-bit number. So that's a number between 0 and 2 to the 64. Well, signed in Java, so between negative 2 to the 63 and positive 2 to the 63. And next long is interesting because this internal LCG, it only gives you 32 bits at a time. So how can you make a 64-bit number? Next long does it by just calling this twice to use 2 seeds. And so the upper 32 bits are one random number, the lower 32 bits are another random number. And this method gets called a lot by Minecraft to seed your world initially. If you don't fill in a seed for yourself, Minecraft just calls next long for you. And also, this gets called internally in Minecraft a lot because every chunk has its own copy of java.util_random with its own little seed that runs to generate stuff within that chunk. So next long is very, very, very important for Minecraft seed finding. The others a bit less so, but they do show up a ton. I'll just go quickly through them. There's next int with an argument of n, and that gives you a random number between 0 and n-1. And it has different behaviors whether or not n is a power of 2. But if we know what the arguments to next int are, we know how many times it's calling that internal LCG. And then we also have next double, which generates a number between 0 and 1. and next float, which generates a less precise number, a 32-bit float between 0 and 1. And so let me explain why knowing how all those behave is important, right? So this is a common problem in seed finding, which is that we have a JavaRandom seed that does something super special. So for example, I've shown on screen an 11-eyed portal, right? So this is around a 1 in 9 billion chance. 1 trillion over 108. Yeah, round 1 in 9 billion chance. And excuse me. We are able to find seeds just before this portal is created that would give us this super rare 11-eyed portal. And this is super important for speedrunning. This is actually the problem that got me into seed finding initially. The problem is that before the game makes this portal, the game asks the same linear congruential generator that's making these eyes, which it asks that generator to make all the cracked stone brick and the mossy stone brick in the walls and randomize all of that. So it does a ton of junk before it even gets to this portal. And that's a bit of a problem, right? Because when you set a seed in Minecraft, you're not setting the seed right before the stuff you want. You're setting the seed ages ago. And then that seed that you tell Minecraft to use has to go through and it needs to generate a ton of stuff you don't care about, like whether or not the bricks are cracked or not, or mossy or not. And then it gets to the stuff that you're seed finding for. So that means that in order to seed find at all, we have to know how much junk is in between when we get to control the seed and when Minecraft actually uses it. So if we can count the junk, we know how much junk there is and we can account for it. So that's what kind of this previous slide is all about, right? All of the most common ways that you're getting random numbers out of JavaRandom are almost entirely predictable how much they use JavaRandom, how much they're going to update that internal seed. And so that's a really essential fact about the way that Minecraft is programmed. But even if you have that count, right, it's very expensive to simulate all, maybe there's, in the case of portals, there's 761 calls we don't care about before we get to the actual portal. If we don't care about that, it's really computationally bad to be simulating all 761 of those little things I don't care about at all, and then getting to the meat, getting to the portal. So ideally, we'd have some way of jumping, just going from point A to point B, skipping over 761 pieces of junk in one giant step. And it turns out such a way does exist. So, and then the other problem is also that if we have something that we know is good over here, where the meat is happening, but we only get control way back in the sequence, we also want a way to be able to reverse the number that we have that's good over here. We want to find a way to be able to reverse it all the way back to where we have control. And so that means not only do we want a way to jump forwards when we're running, say, brute force code, we want a way to be able to jump backwards when we already know what we want the number to be over here, and we need to know what to set it to. And so it turns out both are possible, right? So to see how they're possible, we're going to do a little bit of algebra. So we're going to recall that this is how JavaRandom is implemented. So seed is updated to big number times seed plus 11, divide by 2 to the 48, look at the remainder. And this is going to let us do some algebra, okay? So we're going to forget that in the code seed is the same variable, okay? We're now going to write this out as an equation of relating the new seed that we've been updated to the old seed that we had before. And so we're currently, this slide, we're going to be concerning ourselves with reversing the RNG once. So currently we have a formula for the new seed in terms of seed. What we want to get is we want to get a formula for seed in terms of the new seed, because that will let us that'll let us go from the good stuff all the way back to what it had to be when we had control. So we're going to write new seed is congruent to our big number a times seed plus 11. So, and what I mean by congruent to is I mean that it leaves the same remainder when divided by 2 to the 48 as the right-hand side. So the left-hand side and the right-hand side of that little triple equals sign are congruent mod 2 to the 48. And once again, being congruent just means that they leave the same remainder modulo 2 to the 48 in this case. So okay, that's not surprising, right? And it turns out when you're working with congruences like this with the triple equals, it behaves a lot like equality, right? So if you subtract 11 from the left-hand side and the right-hand side, you can take a moment and convince yourself, but of course they're going to still leave the same remainder, right? You just sort of subtract 11 from each of their remainders. And since they were equal before, they're equal now. So we now have that new seed minus 11 is congruent to the big number times seed. And now what we really love to do, right? So this is very much just regular algebra that you've seen since 6th grade, right? The thing that we want to do here, if we were still in 6th grade, was we would divide both sides by this big multiplier, this 25 billion thing. And that does initially seem like it would work, but the thing is about division is that seeds can only be integers, right? There's a little bit of a weird way to explain it, but if you care a lot about modular arithmetic, I'll link something in the description. It's kind of a bit beyond the scope of this video to explain modular arithmetic in full detail. But you can intuitively think that we have no guarantee that the left-hand side will be divisible by our big multiplier, and we have no guarantee, and we know that we want seed to be an integer because we just can't set it to non-integer values. But we still want to preserve this congruence, and we really, really want to get rid of that big multiplier. We just want an equation for seed alone. And so the very, very clever solution is that instead of thinking about dividing both sides by this massive number, we're going to multiply both sides by a big number, which is this magic number. I'll explain where that comes from in a moment. And this number has this awesome property that multiplied by our a, our special 25 billion number, it leaves a remainder of 1 modulo 2 to the 48. So if we multiply both sides by this massive 246 trillion number, well, on the right-hand side, we have these two numbers multiplied together. They leave a remainder of 1 modulo 2 to the 48. 1 times seed is still seed. And then we can distribute out, and we get this. And also note that I took the liberty of turning a negative number into a positive number. And that's because every negative number has some positive number that leaves the same remainder modulo 2 to the 48. I should maybe have made that more explicit. And so we can see that our big magic number magically solved the problem. If you're wondering where that came from, there's an algorithm to find such numbers. It's called the extended Euclidean algorithm, and it is virtually essential for Minecraft seed finding. We solve a lot of this sort of elementary number theory stuff, congruential equations. But we finally achieved what we wanted initially. We have an equation for seed in terms of new seed. If we multiply new seed by this magic number, we add this other magic number, we get the seed that generated it. And not only that, but if you look closely, you'll see that if we were to transform it back to this assigns to notation, This formula that we've just derived is another linear congruential generator. So every linear congruential generator has a backwards linear congruential generator that does the same thing in reverse. So if we want to, so as long as we know these numbers, which we do in this case, and we can always figure them out quite easily, we're able to go back in time and go from the good part that we want all the way back to the part we have control over. And this also means that if we want to skip an arbitrary number of calls, it suffices to know, to go backwards, since going backwards is another LCG, and going forwards is an LCG. If we just know how to do one LCG an arbitrary number of times very quickly, we'll be able to jump back and forth with the speed that we desire. So we're going to take for a moment, we're going to consider a general LCG, right? We have seed assigned to a times seed plus b mod m. Okay, great. And so in order to ease ourselves into what it's going to look like to call this thing twice, we're going to take this expression for the new that seed just got assigned to, right? So seed just got assigned a times seed plus b. We're going to take that expression and we're going to plop it in for seed. And now we have the seed 2 calls in the future is going to be assigned a times seed plus b mod m. And in modular arithmetic, the distributive property goes through just fine, and we get seed is assigned a squared times seed plus b times the quantity of a plus 1 modulo m. Whew, bit of a mouthful to say there. But again, I would love to point out, we've got ourselves another LCG. So a squared times seed plus, and then b times a plus 1 is now fulfilling the new role of our b was before, and still modulo m. So we've managed to take one LCG called twice and turn it into a single LCG that we can call once. And so long as we know the values of a squared and b times a plus 1, we can always do this. So for the exact same price of operations, one multiplication and one addition, we can skip 2 in a row. And it turns out, same math goes through for calling it n times, right? Now that we've addressed the case of calling it twice, we're going to take a look at it doing it n times, right? So grab our expression, a times seed plus b, plop it in for seed, grab that expression, which we just saw in the last one, plop it in for seed, and just completely plug it in n times. And we end up with this awful nested expression up top, right? A times a times a times a, da, 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 a times seed plus b, da, 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 and then that quantity plus b, and all that plus b, then all that plus b, all the way up, and then remainder modulo our modulus. Whew, bit of a mouthful. And so let's distribute out. Okay, it's a lot of stuff to work with, but it's not that scary. We see that seed is going to get multiplied by a n times, where n is how many times we nested it. So we're going to get a to the n times seed, and then plus some garbage, right? So what is that garbage exactly? Well, we've got one b on the very outside that's never going to get multiplied by a, then plus a b times an a to the first power, plus a b times a to the second power, plus b times a to the third power, all the way up to b times a to the n minus 1th power. And so we can write that using the summation notation that I have down below. So all that big scary sigma symbol means is that we're summing a to the 0th power plus a to the 2nd power plus a to the 3rd power plus a to the 4th power, all the way up to a to the n minus 1th power. And then you multiply that big summation symbol by b. And that's all that expression means, and all modulo m. And if you're familiar with this sort of summation expression, you might actually notice, but there's an easy way to write down that big summation symbol as a certain division. So a to the n minus 1 divided by a minus 1 is just 1 plus a squared plus a to the 3rd plus a to the 4th plus a to the 5th plus a to the all the way up a to the n minus 1. And we do indeed get our formula for skipping n calls. So if we have an LCG
and we want to know the seed n calls in the future, but we don't want to have to do, operate n calls to the LCG, we can multiply our seed by a to the n. We can add b times a to the n minus 1 over a minus 1, and then we can take the remainder modulo m. And of course, this is another LCG. A to the n is our new multiplier, b times this expression is our new addend, and our modulus stayed the same. And it's also got the benefit that these numbers, they're not too hard to find with a program. We actually have a Discord bot that calculates these numbers for us. So if we want to skip ahead or behind n calls very, very quickly, we can ask the Discord bot and it tells us what multiplier to use and what addend to use. But we also have ways to calculate it on the fly if we don't know how much we need to jump before the program is actually running. So this is very cool, right? So we don't need to do a lot of computational work to jump from, hey, I have a seed that does something cool that I want over here, and I want to know what the seed that it started with should be. And that's just an instant. You multiply once, you add once. And once again, I stress the reverse problem and the forward problem. They're the same thing because they're both linear congruential generators under the hood. Okay, so Minecraft does all of its randomness with JavaRandom, which is a linear congruential generator. There are these easy to compute formulas, perhaps not obviously true formulas, but they're easy to compute formulas, which allow us to skip forward or backwards n calls in an arbitrary linear congruential generator. So regardless of the constants of the linear congruential generator, we can plug them into the formulas we just derived, and we now know a way to skip forward or backwards an arbitrary number of calls in one multiplication, one addition. And we also know that because of the way that Minecraft works and because of the way that JavaRandom works, if we look at how the code is written, we can know exactly how much to go forward or backwards when we're trying to reverse a seed or when we're trying to brute force for something that's deep inside the random number generator sequence. And that's about it. Those are the main points that I wanted you to take away. There's one final thing that I'm going to say, and it's that all this time I've been saying that the user has control over what the number that they set at the start is set to. And while that's true, you should be cautious because java.random is a little bit sneaky. They scramble the number that you give it just a little bit to stop you from putting in some dumb number like 0, because 0 is a terrible seed to start with, right? Like you saw how big those numbers could get. They could get as big as 1 trillion. If you plug in 0 initially, you get 0, and then multiplied by your massive multiplier, still 0, plus 11. 11's tiny in comparison to the normal numbers you get. So that would be like 2 very tiny numbers in a row, a 0 and an 11. That's very weird. So the Java developers, to stop you from trying something silly like that, they add this initial scramble where they do what's called a bitwise XOR with the number that you give JavaRandom, or in this case Minecraft gives JavaRandom. Java is going to XOR the number that you give with the multiplier for the LCG. And XOR just means that it's like a pattern to scramble. So when you XOR a number by another number, what you do is you write both numbers in binary, and then where they are the same, you write a 0. Where they are different, you write a 1. And XOR has a really cool property, which is that if you XOR by something twice, so if you give me some seed S, and you give me, and then you tell me seed XOR A, I can find out what your seed was initially by XORing by A again. So when we reverse back, we also need to undo that XOR. So we reverse back from good seed all the way back to the seed which we get to set. And then we have to undo the XOR by this constant to get the number that we should tell Minecraft to give JavaRandom. Then JavaRandom is going to scramble it with this XOR, and then that's the number that we're able to target. And actually, I wanted to quickly point out something as a little bit of a tidbit at the end. This is a bit silly, but if we remember our formula that we found to reverse the linear congruential generator one time, we've got massive number times new seed plus massive number is congruent to seed. And let's find the seed, let's one before this, the seed 0. Okay, so if we put in 0, we get multiplied by a massive number, we got 0, we add it, and we get that massive 107 trillion number as our seed just before the seed 0. And then if we take that seed just before the seed 0, we can XOR it by what JavaRandom XORs it by to get the number that we need to feed JavaRandom, which is this bottom 107 trillion 38 billion. Yeah. Oh. 380,838,084. Yeah. And I'm gonna guess that some people in the audience might recognize that number. But I don't want to, that's my little puzzle today. So maybe some of you have heard about a bug where a seed returns 0 after one call. And this would be the math that you would do to find that seed, is plugging in 0 and undoing the XOR. So maybe some of you recognize that particular number. So that's your puzzle. And yeah, thank you everyone for sticking through. My next video is going to be a video on some RNG manipulation that I've invented recently. Well, we've kind of always known it was possible, but anyway, we're going to be putting a lot of this stuff into practice in game, and we're going to be using it to, well, I don't think I want to spoil that, but cool stuff. There's a lot of freedom to do stuff here once you get the basic theory down. And yeah, so the main takeaway from this video, the main thing that you're going to need to use along with this summary page, main thing that you need to remember is this formula right here, this a to the n times seed plus this garbage mod m. We're going to be using this a lot, like the next video, a ton, because we have to, right? It's probably the biggest weakness of linear congruential generators, is the fact that you can jump forward and backwards so quickly. That's not really something you usually desire in linear congruential generators. Well, random number generators. Well, second biggest weakness, but that's the next video. All right, thank you everyone for watching. Really appreciate it. And yeah, I hope you enjoyed. Ask any questions in the comments. I'm obsessed with this stuff. I'll gladly answer it. I know that I'm a bit rambly with how I explain things, so hopefully I can help out. All right.